I didn't really give much of an introduction to myself. So I'm a PhD student in Oxford working with Arno. I do say I also work with Marco Cotteri and Arash Vada for the last year.
Right.
Okay, so again, the coupling constraint is quite simple, and the discrete setting is just the sum across the rows and the columns. So here the beta, the b's are the probability masses for each of the margins. Okay, so I hope this is fairly straightforward. Right, so what does the primal look like in the regularized case? It's just the dot product of the sum of the costs times by the masses. And the regularization term here is just this part here. Okay. And again, the joules can be simplified rather to be functions, they're just vectors of length n and m. So here, again, I've not put in the dimensions, but say alpha has n particles and beta has m. And again, the joule is again quite a nice format. So when I mentioned people can solve this using stochastic optimization, you can simply sample from the measures and just do gradient descent basically on or you can do full batch gradient descent on f and g. Because this is convex, so the primal is convex in terms of the actual probability coupling, and in the joule it's concave, strictly concave. So you'll always get a solution. Well, you should get a solution. Let me know if I'm going too fast, by the way, if people are writing things. So all of this is in a few references. So there's a book called Computational Optimal Transport by Marco Cotteri and Gabriele Peri. And Gabriele Peri has some lecture notes on this as well, which are online. Yeah. Okay, so what does the actual optimal transport look like? So here's some animation. So here, actually, the regularization term is slightly different. But essentially, it's a coupling matrix whereby the sum of the rows and the columns add up to the various marginal weights. Oh yeah, sure. And essentially what the optimal transport is doing is creating a very sparse coupling between the two measures. So in the continuous setting, in most, under general sort of loose constraints, the coupling will actually be deterministic. So say you have just continuous state spaces and the L2 or the ground cost is just the Euclidean distance, then this mapping will be deterministic, so there'll be no mass splitting. For the discrete setting, this is not the case. So for every row, you'll have at least, well, in general, it's not the case. So you should have some 2 points with positive mass per row. So if you think about transporting from, let's say each of the red lines is associated to a particle or an atom, each atom will be mapped to 2 or more other atoms in the next measure. So yeah. But yeah, I guess the optimal transport part is just creating some sort of sparsity here. I think there's a theorem to show that. So you have this strong duality here. So yeah. Yes. So here in this coupling, I'm trying to pause it. Oh, sorry. So here we're trying to minimize this xi, yj ground cost basically. So each atom so say you have equal weights, say the red lines and the blue lines were the same size, and the x's and the y's were the same atoms, then each x will just be on the diagonal essentially, yes. So say you had just the squared Euclidean cost here for the ground metric. You can decouple this to be essentially minimizing the variance of each row on your coupling matrix. And that way you actually create some sort of concentration, if you like. Okay. So actually, I'm going to talk about this a bit later in terms of particle filtering, or differential particle filtering, which may, I guess, give it more insight.
Thanks.
Yeah, sure.
You mentioned that this problem is deterministic stochastic.
Oh yes, deterministic. Yeah, so it has a unique solution because it's convex. Yeah.
But what if you have imagine if you have a few atoms with same mass from both sides, you can kind of if you have some examples, so you can either move one for the other, or
Oh, so you can split the mass, right?
yeah, it's always unique.
Yeah. So I guess it's the F and G. So okay. So in terms of the dual, the F and G's are unique up to translation. You can always get something separate. For the primal, I'm pretty sure it's unique, but yeah, actually, I'm thinking about this, maybe you can do some linear combination of two equal. No, it should be unique, I think, yeah.
Okay.
So if you have two, so your setting was you have two atoms which are the same.
Yeah.
Where does the mass go? Yeah. It would go, I assume, to each one equally. But it doesn't have to go to, like, this is the whole point. It doesn't, like, even because of this regularization term, it might not even do that. It'll have some sort of blurring going on. So you'll have some mass going to some suboptimal other atom.
Yeah.
So just to make to ensure the constraints are held.
Yeah. You mentioned something about no mass splitting and steep linear cost. So the analog of Grenier in the multi-dimensional case would be with linear cost.
So Brenner's theorem is for the, I guess it's for the squared cost, right, divided by 2. So you just times by 2, right? And you get the same, but not for that. The theorem doesn't exist for discrete settings. You have something. So actually, the Brenner's theorem is much more general. Well, there's an extension to any convex function, so that might be of interest as well. Actually, so it's not just the gradient of a convex function. It can be the, forget the actual term, but essentially it's like an argmin of the cost minus the gradient of a function. Okay, cool. Okay. So yeah, this has a lot of nice properties basically. One, it's the dual is concave in terms of F and G, and the primal is convex, and this is strict actually for any positive epsilon. The F and G are unconstrained, and then so because this has a unique solution, at least the F and G is up to translation. When you reduce the epsilon, you obtain a unique, not non-unique, but a solution to the primal with epsilon equals 0. So because the non-regularized case does not necessarily have a unique solution, what you'll obtain is one of the solution from the solution set with the maximal entropy, which is quite nice actually. So you can essentially you can solve the regularized problem for epsilon and slowly decrease epsilon until you get a primal solution. So visually, if you think of the solution space for the coupling, the regularized case essentially has a sort of ball around it away from the vertices of this the polytope, if you like. So because the coupling in the discrete setting has these constraints whereby the sum of the rows and the columns, you'll have essentially some polytope of solutions, and I guess the fundamental theorem of linear programming is that your solution for the non-regularized case will be on the vertex. And because this regularization term essentially creates a ball around your solution, you'll be away from the vertex. So this is quite nice in some respects that your solution will be a bit more stable. So in the primal setting, if your masses change slightly or your weights change slightly, your solution may jump. In the regularized case, you don't necessarily have that for small changes. It's differentiable. So the primal will jump because it's on the vertex, because it's just a linear program. So the primal doesn't have that term. Yeah. So primal. The non-regularized case doesn't have that term. Yeah. Oh, sorry. Yeah, I'm switching the non-regularized and primal. Yeah. Okay. Yeah. So the non-regularized case will be on the vertex. This is only in the primal setting. So this is just for primals. The coupling. Yeah. The coupling matrix. And I guess for a sort of visualization of what it looks like. So when your epsilon is very small, you essentially have a very tight coupling. And as you increase epsilon, you blur the coupling. So at infinite epsilon, you essentially have your regularization term dominates, and so you don't really have much signal. But I guess, as I'll show later, that actually high regularization is easier to solve. And so you can sequentially lower your epsilon to get better and better solutions. Yeah, this is the coupling matrix.
With more regularization, seems that the matrix is less sparse.
Yeah, exactly. Yeah, so you have this kind of blurring. So I think the sparsity comes from the ground cost, at least for the square distance. So there's some recent work trying to introduce sparsity even further by changing the cost matrix to have some sort of regularization term or some L1 part to it. And that way you can show that in the non-discrete setting, you still have a transport map. Okay, so as I mentioned, you probably noticed if you have read some of these papers that all the primal dual relationships, the regularization term and I guess the extra regularization term on the dual are all slightly different depending on which paper you read, which is a bit frustrating. So the original paper from, the Lightspeed Syncon paper from Kasuri from 2013-14 has one term. The book, Computational Optimal Transport, has another regularization term. And then some of their PhD students have papers with different regularization terms. So it's a bit of a mess. So, but roughly, they can all be worked out. So it's not too bad. And most of them look a bit like this. So if you have this primal and dual, the primal has some regularization H, and the dual are, for the discrete setting, you can just do Lagrangian multipliers. And you'll see that the actual potentials, F and G, or potential vectors, are the Lagrangian multipliers, which is interesting. So for the regularization term I described at first, essentially this entropy term, you'll have the corresponding. So if you solve these first order conditions, so set this part equal to 0 and solve. You get the following sort of primal dual relationship and the following regularization term for the dual. And again, another one, which is, I guess, is a bit more standard nowadays, is to add this this KL with respect to the cross alpha and beta. So that this seems to be a bit more stable, I suppose. And it alters the primal dual relationship as well as the regularization term by just adding your alpha and beta here, or your A and B, and A and B.
The original version you got on the first slide was actually the second one.
So the generalized version, yes, was the second one, and then the discrete setting was the first one. So I copied the discrete setting from the book, basically, the computational OT book. But yeah, in general, I think the general setting people tend to use the second one. For general measures, for discrete, I guess people switch between the two. But there's more than just this. So people can, if you ignore this -1, there's another. Essentially, you'll have another minus epsilon in the exponent here, or -1 afterwards. I think, can't remember which way.
First case corresponds to like a KL product like a uniform.
Uh,
So it's not.
so it's just an entropy, I suppose.
So these would have the same multiple fees?
Yeah. But just different. Yeah, exactly. Which is kind of weird. Yeah.
It's the sum of the IJ, PIJ, and log AI, PJ, sequential number.
So essentially the regularization term for here, okay, wait, actually, so would it be the same? Yeah, because essentially this is just a constant, right? The AI and BJ are fixed. So you take the log out and the sum of the PIJ is just equal to fixed as well.
Historically, in the middle column, you could sort of bring the AI and the BJ up into the exponential.
Yeah. So it's good to be aware of this because I always panic that I've made a mistake and have A and B's somewhere where they shouldn't be. So no one ever writes this. I've never seen any paper where they explain there's various different ones. I think the best resource for this is there's a PhD thesis from Aude Geneve from 2017 or 2018, where she goes into detail about the different regularization terms and also introduces other ones such as a quadratic regularization as well.
So this equivalence also holds for continuous memory, like continuous distributions.
So
like, do you still have this thing where people have two ways of writing down the regularization term? But they're not.
so I think I think you can do, yeah. So you can I guess
you still integrate to one and you still get that as a constant.
yeah, I think I've not really seen it for the continuous setting, because I think a lot of people tend to use the bottom one that I've seen, but maybe there's some cases where they do. I guess there's not an awful lot of work on the continuous setting for in this framework because there's not much you can do. You have to use stochastic optimization, and it's not very satisfying basically. And then I guess the Schrodinger stuff is quite different from looking at the primal or dual directly. What's that? Oh, vectors of what? Sorry, I can of one. So that they're just probability masses, right? So they sum to one. They're the they're the marginals. So they're here. So the alpha is AI. I can't remember how many slides I put on this, so we'll see. Okay, so this is kind of the whole framework, and now I'll actually talk about synchron algorithm. How do you actually solve this? Okay, so back to discrete measures. Again, you have this primal dual relationship. You can express this in terms of some kernel. So I guess this is people call it Gibbs kernel. That's correct. And your primal, extrapolating from the term on the left, you can express your primal in a vectorized form as the essentially diagonals of. So take this vector mu, which is just your exponential fi divided by epsilon, and your v, which is the exponential gj over epsilon as a vector. You can express your coupling p as just a product here. So the diag is going from vector to matrix. And we know that the marginals should sum to A and B of this matrix. So here, this dot is the element-wise multiplication. So these are the constraints that we have. So the first so I'm going to talk through 3 equivalent formulations of the synchron algorithm. And hopefully they'll start to make sense. So this is the standard, I guess this one was very popular in the first sort of iteration of synchron papers, but it turns out to be less stable than the others. So the actual iterations are essentially taking this, the marginals, and essentially taking your the KV, so the dot product here, to be into the denominator, and this is an element-wise division now. So essentially, I'm just doing this sequentially. So what is this really? This is essentially just renormalizing to match the marginals at every iteration. And I guess I've not mentioned it here. Where do people start? What is the original U and V? There's a lot of options. Like, you can choose what they want essentially, but the standard results are in U and V's to be 1.
Vector.
Yeah, vector. So U again is of length n, and V is of length n. So it's essentially the exponents of. So if you look at these two here, it's the exponents of Fi over epsilon. And U is so this U here is this part, and this G, this V is this E to the Gj over epsilon. And so what's quite nice here is that everything is parallelizable, so vectorizable at least. So it's an iterative scheme, but each step is vectorizable across the n and m. So it's quite nice to work on a GPU. So the complexity of this is n squared because you have this kernel vector product, but because it's vectorizable, it's quite fast, and it looks more like n log n, I think, when you parallelize this. So that's quite nice. What other things? So I guess this is a fixed points method as well. Essentially in the joint of U and V. And rather than doing these sequentially, you can do these updates jointly and it will still work. Yeah, sure. So I'll go into why it works in the next step. But essentially it can be viewed as a block gradient ascent on your F and G, and just reformulated. And it can also be, I guess, these are related to KL projections as well. So the equivalent of Bregman iterations, which again, I'll talk about in the next step.
The synchron algorithm, the synchron learn, once the fact that you can parallelize the bisynchron.
Oh, that's just the name of the person who this, yeah. So I think this was rediscovered loads of times by various people, but I think Synchron was in the 60s, and I guess that name stuck. Oh, Synchron NOP, I think people call it KNOPP. And the more general version was called the IPF, or iterative proportional fitting. So I guess there's a Wikipedia page on IPF. And I think that was, again, I think it's been rediscovered a bunch of different times. Okay. So this is the matrix scaling or vector scaling version. Essentially, again, this is just taking your matrix P and projecting on one marginal, and then taking the next and projecting on the next marginal iteratively. So yeah, actually, I'll talk about the KL projections. So talk about, well, when I talk mean KL projections, I want to talk about the closest coupling P to some other coupling Q, such that P is in some set. So for this measure, if you like, e to the exponent Cij, well, negative Cij, your optimum coupling is the KL projection onto the set whereby the marginals are correct. So the sum of Pij is A and B. Okay. And then this can be decomposed into two different sets, and the intersection will be the marginals being correct. So this is the Bregman iteration interpretation of this. And so the Synchron algorithm essentially consists of two alternative Bregman iterations, so it's KL minimization steps. So I probably should have written down the actual KL for the coupling, but essentially it's like looks like the entropy term minus the coupling entries and plus the other coupling entries. Yeah, sure. So this is actually not a very useful, it's not a very practical formulation of the algorithm, but it's just to get, it's the same algorithm, but it's just to give a different intuition behind it. So there's a theorem like the Bregman iteration theorem, which shows that this will converge basically. Because of this interpretation, the synchron algorithm will converge. And these projections here are actually essentially to find the closest coupling from a previous coupling, which satisfies these marginal constraints, is just scaling to satisfy the constraints. So that's the that is the KL projection. So I think I quite like this because this links directly to the Schrödinger bridge, which I'll talk about in a bit later. So this is a good interpretation to have. Okay, so I'll go a bit faster. And the third sort of interpretation is this block gradient descent. So this is the dual objective, which we talked about earlier. It's just the sum products of Fi, Fg's, and the weights with the entropy rectified term. If we take the first order conditions, so take the gradient with respect to Fi and G, Fg, set it to be 0, one can solve essentially work out what your for each G what your F should be and vice versa. And if you look at this, so essentially if you take the gradient with respect to F, like you just get the A and some term here which corresponds to this. If you set this to be equal to 0, you essentially recover these projections we talked about 2 slides ago. And because this is convex, this block gradient descent will converge. So these aren't the updates, these are the first order conditions. The updates will be on the next slide. Yeah, just set them to 0 and solve for F or solve for G. Yeah, so you're just solving the like instead of a gradient, you actually can solve it. So you're solving for when it's equal to 0, rather than just doing the gradient step. Which I think is quite intuitive to me. So essentially, it's an optimization algorithm. Yeah. Okay. So when you actually rearrange those block gradient descent steps into your updates, it looks like this. Here, okay, I copied this from a previous paper, but here the omega is a momentum term. So if you set this to be 1, you get the general setting. You get the previous setting. So the algorithm consists of setting your potentials to be, it can be anything you want. I think that's a crucial thing no one really talks about. So actually, I had a paper recently talking about that, saying you can do a lot better than setting them to be 0 by choosing a very similar OT problem, which is easier to solve, like the Gaussians, or for one-dimensional solving the sorting problem, or solving an OT in the space of measures, for example. So yeah, I guess so. Yeah, I guess it's a bit more. Adds essentially your gradient. Yeah, so it's like momentum in your gradient descent. So it's taking the previous F and adding, I guess, yeah, a bit more like a step size, I suppose. This momentum adds stability as well, because each step will be close to the previous one. So yeah, actually, so the complexity is n squared. The potentials can be anything.
Okay.
Because they're invariant translations. So if you add F, add a constant, like a big constant C, and G minus a big constant C, you'll have the same coupling. You have the same solution. So C can be anything. So C is very big. These potentials could be a bit crazy. So yeah, and I guess the point that I want to make again is that this is differentiable. So because this is all all these steps are just matrix multiplications. So you can take the gradient all the way through all the iteration. This is a bit naive, but people have done it, and it seems, and for a very small number of iterations, it works. For a large number of iterations, this gradient will become quite unstable because you have an accumulation of numerical issues. So there's ways to get around this. Oh, so yeah, so one of the reasons the synchrone algorithm is quite popular is because in the machine learning circles is that it can be embedded within like a neural network or a differentiable procedure. Hence, you can take the gradient through, and it can make things differentiable. So one nice example is like a sorting operation. So a sorting operation, if you use quicksort or something, but the sorts lots of if statements, this won't be differentiable. If you perform the transport problem between the atoms you want to sort, so x1 to xn, and the ranks, so y will be 1, 2, 3, all the way to n. So you're solving the transport problem between n particles and n ranks. And if you apply synchron to this, essentially you're mapping the biggest xi to the biggest y, which will be n, and vice versa. So essentially you get a sorting algorithm. And because the synchron is differentiable, you get a differentiable sorting algorithm. So why is this useful? That's a good question. People can use it for like top k loss and to optimize with respect to the top k loss. I guess it can be used for ranking. So say you want to optimize for second place, you can come up with an algorithm, like an objective to optimize for second place. Oh, here's another one for conformal inference. People are familiar with conformal inference. Essentially, you have a holdout set, and you look at the quantiles, and you evaluate your classifier, if you like, on this holdout set, and you have some theoretical guarantees based on how your quantiles are doing. And so you want to say if you want to optimize your classifier with respect to these quantiles, you need a differentiable and indifferentiable way. So optimizing a classifier with gradient descent or something. You can take these quantiles and make them differentiable using this differentiable sorting operation. So I think that's quite a nice use of differentiable sorting.
Sorry, do you mind just quickly going through again why the synchron, the sorting?
Oh yeah, sure. So since I was an undergrad here 10 years ago, so no, not less than 10 years. So you have your something you want to start. So you have an array x1 to n, which could be anything. So here it's 1 to 4, these x's. And say you have a straight line. This could be like 1 here, 1 here, here, 1 here. I remember them. Now, say you have so these are all equal weight. So you put some probability mass to each of them, one of theirs, so they equal probability mass. Now, to create what you need for a transport problem is the particles for 2 different measures and 2 different sets of weights. So create a new set, y, which is just 1, 2, 3, all the way to n, so the actual rank. And so you want to do a transport problem between, and these are all equally weighted as well, of 1 over n. So say you want to do a transport problem between these, between x and y, 1 to n. This can be any increasing set of collection, if you like, as long as it's 1 to 1. Because there's equal number and each have the same weight, the optimal coupling will be mapping each one of these to each one of these, but depending on which one's closest. This is what this is trying to show here. And essentially, the biggest x will get mapped to the biggest y because that will be the closest, and vice versa. So essentially, you'll have a sorting procedure. Obviously, it's slower than sorting. Sorting is n log n, right? For quick sort and things. This will be n squared, but it's differentiable.
Yeah.
So this is what you get from it. So similar to sorting, people can use differentiable clustering. So again, rather than 1 to n, so you have just clusters, so k clusters. The transport problem will cluster your will have a soft assignment between your x's and your cluster centroids. And so, yeah, I guess you maybe want to learn the centroids as well. So it's good that it's differentiable.
How many iterations?
So for sorting, it's pretty bad. So sorting can be between 100 to 1,000 iterations. For some problems, so people embed these synchron layers within VAEs and all sorts of things like this. So it depends on the complexity and how far your particles are away from each other. And your initial, okay, there's a theorem which I haven't included. It depends on some sort of conditioning of your condition number of your cost matrix of the kernel, so the exponential to the cost matrix, and how close you are to the solution. So it looks something like the distance between F, L, and your optimal F bar. So this is the variation norm, which is like the max of each element minus the min of each element. I think this is something like condition number of your kernel K to the L times by the difference between your starting points H0 and the optimal. So if you have a good initialization, this should be reduced. And typically people run synchron until you get good thresholds. So this is some work I did was choosing better initializations to make this smaller. Other work tries to reduce the condition number. Not very much, not very many works. Yeah, this is kind of the problem. For some problems where, say, your measures are close to Gaussian, synchron, people have reported good performance with synchron with just like 2 or 3 iterations. Because essentially it becomes like a k-means, essentially, like a clustering type problem. So it's very easy to do. Okay, and so rather than taking gradients all the way through the synchron procedure, people can use implicit differentiation. So because it's a minimization problem or a maximization problem, essentially it becomes a fixed point update. So H here is your gradient update, if you like. So say, okay, I found notations from something else, but essentially your psi here is your F and G joint together. So your optimal F and G and H will be your synchron update. So at optimality, the update won't change your F and G, your psi here. So yeah, say you take the gradient through your fixed points part and solve, you essentially realize that the gradient through the solution of your optimization problem doesn't depend on the trajectory of your optimization problem. So this is just taking the gradient of the top equation and then rearranging. So this is quite nice. So it means if you're using TensorFlow or something like this, or JAX, you don't have to trace the gradient through the whole synchron operations, which is quite slow and memory expensive, basically. So you can use this, plug this in as your gradient, and then plug it into your whatever you like. So this is quite a nice trick for using optimization for lots of things. So not just synchron, but any argmin layer, if you like. But this speeds up synchron about 3 times. So it makes a huge computational savings. Yeah, so the gradient doesn't depend on intermediate states. Also doesn't depend on the initialization of your synchron algorithm either. So you can choose your initialization to be whatever you want. And if you have a good idea of what your solution will be, or say you have multiple problems which are all kind of similar, you can learn a good initialization. So a paper from Brandon Amos recently did try to learn the initialization with a neural network. And it seems to have good results. The problem is the neural network is expensive to train, more expensive than synchron. So practically, it's probably not the most useful unless you have many, many synchron problems and you kind of amortize across the whole spectrum of problems. Okay, Practically speaking, there's a few good implementations out there. So the one I've been working on is Objects. Geom by John Fetty is very good. It's in PyTorch. And I think there's less flexibility with this, but it's all done in C++ with PyTorch, the front end. It's very fast. I think he uses this for shapes. So points on a shape, and they can run sync on very quickly for like 10,000 different points. So it's very good. And people use this for like brain imaging and stuff like this. And POTS, so Python optimal transport tools. So I think this is the most commonly used, but I'm not a huge fan. Okay. Actually, I can go into if we have time, so I'll try and finish fairly quickly if you want a break. So there's a section on tutorials. So this is running transport between point clouds of word vectors. So imagine you take a word and embed it into some high dimensional space, as that's your atom, and then each word has the frequency of that word in your text is your weight. So then your document essentially becomes a distribution. So essentially, what this does is creates a cost matrix, and you can choose the algorithm. The package lets you specify your cost function. So it's not just the squared Euclidean. You can do whatever you want. The default is actually the squared Euclidean. And then specify your sync on what you want to run. And I guess it computes it very quickly, and it handles everything for you. So it handles the implicit differentiation. It handles the iterates in a very stable way using this log dual scaling, and it runs pretty quickly. And it works on GPU out of the box, so that's quite nice. And people have used this again for like single cell genomics, for soft sorting. So this is what I talked about earlier. The soft sorting people use for like the top K loss as a training objective. Yeah, so I guess it's good to have these references in case people want to use them. So the synchron is it handles the choosing of your regularization term as well, because I guess your problem depends on your regularization, and there's options to potentially scale your regularization to the difficulty of the problem, which helps a lot. So all these little tricks make a huge difference when it comes to actually running this for real problems.
Adaptation instead of like to approximate the unregularized as well, or is it?
Well, the regularization, I should have mentioned this, essentially it depends on the scale of your problem. So it depends on your cost and so the relative scaling between your ground cost term and your regularization term depends on your ground cost scale. And so epsilon 0.1 will be different depending on your different ground costs or different supports, right? So essentially you can scale your epsilon to be like the diameter of your point clouds.
So it's not necessarily about getting the unregularized.
No, not. And but again, there is an implementation of this epsilon decaying. So you can get a non-regularized version by essentially specifying a decay schedule going from whatever to whatever. But all the tricks like momentum and Anderson acceleration and smart initializers are already implemented, so it works quite well. And they had the engineer at Google doing all this stuff, so I think it's reasonably well implemented. It's a good question. I think essentially it's just a multiplier, say like 0.9 or something. So when I tried doing this, I actually didn't really find epsilon scaling to work very well. But yeah, essentially every few iterations, you change your epsilon. And you don't recycle, so start from the previous potentials and then change the problem. Yeah, exactly, yeah. Okay, sorry, no, I'm not sure. Something else which I guess GMLOS does is multi-scale transport. So say your N and M are very big. You can subsample the N and M, run synchron for the subsample problem, and then there's an unbiased, essentially it's like a kernel interpolation on your potentials from a small N and M to the large N and M, and which essentially looks like a kernel or a Gaussian process basically. And that can be used for the next synchron iteration with the larger N and M, so larger point clouds. So essentially you go from small point clouds to progressively bigger, and this helps like quite significantly, especially as the complexity is n squared. You really want to only use n squared when you're already quite close to your solution. But these are all kind of tricks, but they're very important for real world use cases where you have a large number of points. Okay, so probably now is the time to have a good break, and then I'll talk about the application of particle filtering afterwards. I realize, if that's okay.
It should be 10:30.
Yeah.
So it's 20. Very good.
By the way, does anyone else need to go to the train station after lunch? I was going to ask Paul if there was a taxi or two. Okay, how many people? Two. Okay, so I guess we need two taxis then. What rough time do you guys speak through there?
Yes, don't actually know the time. I think there's trains going on.
Oh, yeah.
I'm also driving to Oxford if anyone needs a lift.
Oh.
Yeah, you're more than welcome.
So kind of, I think so, yeah, your data lines. It's not